So review. So we've got question 7 says, a stone is thrown vertically upwards from a point that is 12 meters above the sea. It then falls into the sea below after 3.4 seconds. And the question asks, it tells us air resistance is negligible. So again, we have permission to sort of neglect all of the effects of air here, which really do make an effect. At which speed was the stone released when it was thrown? All right. Stone is thrown vertically upwards from a point that's 12 meters above sea level. All right, so let's draw a picture out here. We're sort of like on a cliff, and we throw a stone up in the air, and it's like we're right on the edge of it. So it falls up and it goes up, but then it falls all the way down into the sea below after 3.4 seconds. Okay, so we're 12 meters up here. And we know that the total time in the air is 3.4 seconds. And we're trying to solve for the initial velocity u. Right? So we throw a stone up in the air with initial velocity u, it goes up and it falls all the way down past where we released it to the sea below. And we're trying to solve for the speed here. We could use the equation, maybe, S equals UT plus 1/2 AT squared, because we know the net change in position. It had a net change in position of 12. Even though it went up and fell back down, it still has a net change in position of 12 because it started here. And we know the time, thankfully. Remember, we had to solve for the time yesterday. We had to use the quadratic formula. We had an equation like this, and we were given everything besides the time. So thankfully, they give us the time here. We know gravity's accelerating it. So that does it, right? The only unknown there is the initial velocity. So that equation would solve it for you. There's other ways to sort of go about that. Sort of breaking down the motion sort of piecewise. Say like, okay, well, from launch to the top of the display, or from there down, you know. But anytime you can start to see like one equation that sort of solves it, that's usually the most efficient path to the solution. Usually, not always. All right, so let's be mindful of, you know, knowing is only half the battle, right? It's like you know the equation, but you gotta also know sort of how to use it. We gotta have the sign convention proper. So this thing is dropping 12 meters, right? We're launching it with positive initial velocity u, and we know that it stays airborne for 3.4 seconds. We're really subtracting away this term here because a is going to be negative, but like just to see like where it comes from, I'll say plus the 1/2. The acceleration here is the acceleration due to gravity, right? Negative 9.81 meters per second squared, and then the time is still 3.4 squared. We kind of fit it in there. All right, and so we should be able to solve this for you. I'm going to go ahead and evaluate this term first. So we can go 0.5 times negative 9.81 times 3.4 squared equals. And so this term is negative. It's negative 56.7. And the units would be meters. Okay, again, it all solves for displacement. U times t solves for the displacement from the initial velocity. This solves for the displacement from the accelerated motion. So we have 3.4 u minus 56.7 equals negative 12. Perfectly solvable, right? Add 56.7 meters to both sides. This is negative 12 meters. So we can only add and subtract quantities that have the same units. Like you could add 12 feet to 5 inches and be 12 foot 5 inches, right? But those are different units. You have to leave your answer like that. Like you could say, I'm 6.5 feet tall, 6.5 feet. I could say I'm 6 foot 6 inches. I'm adding sort of different units together. I can't just say, oh, I'm 6 feet plus 6 inches. I'm 12 tall, right? It doesn't work like that. Okay, the units have to agree if you're adding them. Otherwise, you just leave them separate. I'm 6 feet and 6 inches tall, right? Like our units for acceleration here in America, what are they? Because like we have U.S. customary system, right? So we say like meters per second squared. Those are the units of acceleration. 9.81 meters per second squared. But in America, how do we talk about acceleration? We say a car can go from 0 to 60 miles per hour in 8 seconds. The units we use for acceleration in America are like miles per hour per second, right? That's a change in speed per time. So when you hear a commercial say, this car can go from 0 to 60 in so many seconds, it's really telling you how it can accelerate. Force is required to accelerate, saying I've got a lot of horsepower in my engine that can cause acceleration. So that's kind of odd units, right? Because it's not like the unit of time here and the velocity is hours, but the unit of time in the denominator is seconds. Or in the metric system, it's just the same unit of time, right? Meters per second, like the change in velocity. Gravity speeds things up 9.8 meters per second. Every second it falls. Every second this stone falls, it's picking up this much speed. Or it's decelerating by that amount when we throw it up in the unit, right? So it's a constant acceleration. See how this term is negative, okay? There are times, though, we talked about this yesterday, there are times you can substitute in where this will not be more negative than this term, right? And that would solve for all the displacements here above. But as soon as we sort of get to the time where it's going to sort of match its original displacement, those terms will be equal, and we'll get a displacement of 0. And then the negative term will dominate the equation, and we'll get, obviously an answer here. We're solving for the velocity, right? But we're sort of saying, well, we know it fell 12 meters below, right? So that's how we sort of end up getting a negative displacement. Negative 12 plus 56.7. Gives me 44.7 meters equals 3.4 U. Remember that this is seconds, right? This was the 3.4 seconds of time. So when I divide by 3.4 seconds, divide by 3.4 seconds, I get meters per second, which are indeed units of velocity. And so the velocity would just be 44.7 divided by 3.4, which hopefully is an answer choice up there. 13 meters per second short. If you're 12 meters above sea level, and you throw a stone in the air, and air resistance is negligible, and it hits the ocean after 3.4 seconds, there's only one speed that you could have thrown that stone with, and it is 13 meters per second.